So here's a few things that are different for this chapter with torque and pulleys. All right. So we did a problem like this earlier where this is the person, they were holding on to the tree and they let go, and this was their lab partner. Okay. We did that lab with the glider. Okay. Okay, so here I have two masses, all right. Here I have a pulley, but now what's different is the pulley is not plastic. Okay. It's metal. Okay. It's still frictionless, still rotates about the axis rotation frictionlessly, but now the pulley has mass. Okay, it's heavy. It's part of the system. It's going to have rotational energy. Okay, as it rotates. Okay, so I have the forces. I drew the forces on each mass. Okay, so this tension pulls that one to the right. Okay, I have M2G points down. This tension is preventing M2 from hitting the ground. All right, but what I want to show, what we didn't have to worry about in the Newton's second law chapter, is now I'm going to draw the forces here on the pulley. Okay, so if I look at the forces that act on the pulley, all right, so what I did here is I just isolated the pulley and drew the forces that acted on it. Okay, so this tension 2, okay, points down. Okay, now careful, that one acts on mass M2. Okay, I'm drawing the forces that act on the pulley. That one's points down. Tension number 1 up here, okay, that acts to the left. Okay, tension 1 is trying to prevent the pulley from rotating. Okay, now there's the weight of the pulley. All right, now if you look at what would be the direction of T1 and T2, okay, so if I just added T1 and T2, okay, they would be off. The net force would be off in that direction, maybe in the third quadrant. Okay, all right. So T1 and T2 are trying to take the pulley and move it, okay, jam it that way into the axle, okay, into the support point, okay. And then I add mg to it, okay. So if I add up these three vectors, T1, T2, and mg, they're somewhere, the net force is somewhere in the third quadrant, okay. So because of that, there's a reaction force, okay, so imagine this thing is pivoted on a nail. Okay, the reaction force is the normal force, okay, because the pulley is not moving. So T1, T2, and mg are trying to yank the pulley in that direction, and the normal force prevents that from happening. So that's why the normal force is off somewhere in the first quadrant. Okay, it's in some weird direction. Okay, so but the normal force and mg don't cause a torque about axis A. They pass through the axis of rotation. Okay, so what's different is when I look at the pulley. Okay, and I didn't draw the normal force in mg. I just drew the T2 and T1. Okay, so as this thing falls, okay, the mass is accelerating. So if the mass is accelerating, okay, that little mass is accelerating, well, that means the string is accelerating. And if the string is accelerating, that means that the rim has an acceleration. And that means that the whole object has an angular acceleration alpha. Okay, but we know from Newton's second law that if there's an angular acceleration alpha, okay, that's some number, that means there must be a net torque. Okay, so if there's a net torque, that means that tension 2 has to be bigger than tension 1 for there to be a clockwise torque. All right, so that's the big difference in this chapter, is that the tension can actually be different on both sides of the pulley. Okay, so here the pulley isn't just there to bend the string. Okay, it's actually there to cause the tension. Well, it causes the tension to be different. So these two, so these two strings, okay, or these two tensions, T1 and T2, because T1 or T2 is bigger than T1, okay, it actually causes the pulley to spin faster. There's a net torque on the pulley. So that's the main thing about this chapter, is that you can't just call this one T and this one T. Okay, you have two different tensions on both sides of the pulley. Okay, that's the picture I have here, right? Since this thing has an angular acceleration alpha, right, there's a net torque, and if there's a net torque, that means that one has to be bigger, okay, than T1. Okay, so in this case, the string doesn't slip over the pulley. Okay, the string actually grabs hold of it. Okay, grabs hold of the pulley, right, can actually pull harder on one side. So T2 is pulling harder than T1, and it grips the pulley and causes it to spin faster. All right, and we're going to see that because the pulley is now spinning faster, okay, and it has mass, it has weight, that now, besides the kinetic energy of the blocks, okay, and the potential energy as it falls toward the ground, that the pulley is going to have a rotational kinetic energy of 1/2 I omega squared, where that's the moment inertia of the pulley, and that's the rotational speed of the pulley. Okay, now, we've done problems like this, all right, in an earlier chapter, but the pulleys were just there to bend the forces, okay? So here I have two masses, and mass 2 is bigger, so M2 is accelerating down, M1's accelerating up, okay? And these pulleys are no longer light, okay, they're frictionless, but each pulley has mass M, radius R, moment inertia I, okay? So I want to find the acceleration of each person and the tension in each segment of the rope, okay? So looking at the picture, I have two different people, okay, but they're connected by the same rope, so there's only one acceleration, all right? Now, how many tensions do I have? Well, I have one there, I have one there, and I have one there. Okay, so I have three different tensions. Okay, so that's how I label them: T1, T3, and T2. So these forces are the force on person 1. These forces are the force on person 2. Okay, so I'm trying to find the acceleration in T1, T2, and T3. So I have 4 unknowns. Okay, so I applied F equal ma to each person. Okay, there's my coordinate system. There's my coordinate system for that person based on the 5-step method. So I applied F equal ma to person 1. Okay, T1 points up, M1G points down, okay, for this person, all right, and that's equal to M1A, all right. So there's 2 unknowns, T1 and A. Okay, so I do F equal ma again to person number 2. Okay, so there's my coordinate system that points down because they're accelerating downward. Okay, downward's positive. So I have M2G minus T2 is equal to M2A. All right, so now I have another unknown. So I have T1's an unknown, A's an unknown, and T2's an unknown. So now I have 3 unknowns and 2 equations. So the math department says you need as many equations as you have unknowns. Okay, so now we do is what we deviate from the earlier chapter, because now we have Newton's second law for rotational motion, is we draw the forces that act on each pulley and apply F equal ma in rotational form. Okay, so what I did is I drew the forces on each pulley. Okay, so this one here, okay, I drew the forces on it. Okay, so if you look at my picture here, okay, T1, that force, the way that's drawn, that's a force number 1, right? Pulls number 1 up. But down here, okay, it's trying to prevent the left side pulley from rotating clockwise. So that's why T1 points down. Okay, this string is trying to rotate the pulley clockwise. That's why T3 points that way. There's the weight of the pulley. Okay, there's a normal force. That's the reaction force of T3, T1, and mg. Remember, T3, T1, and mg are trying to yank. If I add up those 3 forces, okay, they'd be over in the 4th quadrant. And so the normal force N1 is the reaction force to those. Okay. Okay, and then I did the same thing over here for the pulley on the right. Okay, so this T2, okay, that's a force on M2. It prevents him from falling. But if I draw the force on the pulley, T2 is trying to rotate the pulley clockwise, and T3 is trying to prevent that from happening. So these are the forces. Same thing for N2, right? That's the reaction force due to the tensions and the weight. Okay, and I set up here the normal forces and the weights of the pulley don't cause a torque about their axles. Okay, so I'm going to apply Newton's second law in rotational form, okay, about axis A. And again, I know the whole system is moving clockwise. So clockwise is positive for that one. Clockwise is my positive angular acceleration for that one. Okay, so I'm applying net torque equals I alpha about axis A for the left side pulley. So I'm looking at this pulley, okay, and again, torque, force times moment arm, Okay, so T3, and again, my positive direction is clockwise. So what exerts a positive clockwise torque? That'd be T3. The moment arm is the radius, right? So the string always comes off the pulley tangential to the radius. Okay, so that's always a freebie. Your moment arm is the radius. And then T1, okay, that's a negative torque. It's trying to rotate. Remember, it's not rotating the wheel counterclockwise. It's trying to rotate the wheel. Okay, so T1 exerts a counterclockwise, a negative torque. Okay, so those are my two torques, and that's equal to I alpha. Oops, my moment inertia about axis A times alpha. Okay, now I'm trying to find the three tensions and A. Okay, my four unknowns. Now I got this alpha. Okay, so how do I get rid of the alpha? That's the last example we did. We said, okay, that the acceleration of the person, okay, acceleration of the person, acceleration of the person up here, is the same as the acceleration of the string, because they're attached to the string, but the string is coming off the rim of the pulley. So the acceleration of the person, A, is the same as the tangential acceleration of the rim, which is R alpha. So I make a connection between what the pulley is doing with the alpha, okay, and what the acceleration of the person is doing. So right here we're having alpha, okay, I can put in A over R. Right? So that's what I did right there. So where the alpha here is right there, I put in A over R. Okay, and then I divide it by R. Okay, I didn't cancel. I divide it by R. That's why I have R squared. All right, and then I did the exact same thing with pulley with axle B for the right hand pulley. Okay, I applied net torque equals I alpha about axis B. Okay, so T2 is a clockwise. That's a positive torque. Okay, so T2 times moment arm. T3 is a negative torque because it tends to try to rotate it counterclockwise, right? That's a clockwise torque. That's a counterclockwise torque. Okay, that's why it's negative. Okay, and that's equal to I alpha. Okay, and then I use this, okay, that alpha is A over R, right? So the acceleration of the person, okay, is the same as the tangential acceleration of the rim. So A is R alpha. So where I had my alpha here, I put in A over R. Did that right there, and I divide it by R. Okay, so what I did is I summarized. So equation 1 was from F equal ma number 1. Equation 2 is F equal ma number 2. This one was for F equal ma in rotational form of the left pulley. That one was the same, net torque equals I alpha to the right pulley. And now I have 4 equations, 4 unknowns, T1, T2, T3, and A. Okay, and the easiest way to solve this is you add them all together, because here I have a coefficient of 1, coefficient of minus 1. Okay, here's T2, coefficient of 1, coefficient of minus 1, and so on. So if I add these all together, and again, that's the same as solving this one for T1, putting it there, solve this one for T2, put it there, okay, and then insert there for T3, okay. It's a big mess. Okay, it's easier just to add them all together. That's what they showed you in algebra class. So if I add them all together, you can see the T's on the left side all go away, and you're left with an M2G and a minus M1G. So M2G minus M1G. And on the right side, you've got 1, 2, 3, 4. Okay, and I keep leaving off these. That's okay. Okay, and it doesn't have to be I sub A, right? Because the pulleys are identical. So I don't need to write I sub A, just call I. That's the moment inertia of the pulley. Okay. All right. So on the right side, I have 1, 2, 3, 4 things. So 1, 2, whoops, and there's my G. Where'd my G go? Right there. Okay. So I have my, oops. Yeah, I have my M1, oops, get rid of that. I have my M1A, I have my M2A, and I have that one that goes there, and I have that one that goes there, okay? And then all I did is I have an A in every term, so I factored out A, okay, just did the algebra, all right, factored out A, okay? So that's the acceleration of each person, and then to get the tension, okay, it's a big mess, I took this A and I put it back into equation 1, oops, put it back in equation 1, solve that for T1. Okay, it's a big mess. And then I took A and I put it back here, okay, right there, and I solved that for T2. Okay, it's the big algebraic mess because you have to get a common denominator. And then I took this A and I put it maybe over here somewhere, okay, and I solved that for T3. Okay, and it's a big algebraic mess, all right? Okay, so as you can see, all the tensions are different. T1, T2, and T3 are all different, okay? Now, earlier in the semester, we said there's always a couple ways to check to see if your answer makes sense. One of them is check the units, okay? You can check the units, so dimensionally it's correct, all right? Okay. Now, what you can do is, the other way to check is in the limit where something gets big or small, okay, to get some result that you expect. So in the limit where the pulleys are light, okay, from one of the earlier force chapters when the pulleys are just plastic, okay, meaning they're light, they have no resistance to rotate, so their moments of inertia are 0, okay. So if I put in I is 0, 0, 0, right there, okay, turns out that that's what I get for all of them. So in the limit where these metal pulleys become the earlier chapter 5 pulleys, okay, they're just there to redirect the string, then I get the same result I would have gotten in that earlier chapter. I think we did get in the earlier chapter, that the tensions are equal, all right? So that's one way to check your answer. Okay, look at it in the limit where the pulleys become the old style pulleys, okay, where they just rotate without any type of resistance, and this shows the tensions are all the same.